All right. Okay, so today we're going to be starting part 2 of the course. And we're going to be quantizing quantum field theory. So we're going to be quantizing field theory and discussing quantization. So because I always start every lecture with a review, and we started our conversation about quantization in lecture 2 when we talked about the theory of phonons, quantum sound. It's good to go back and do a little bit of review of that, and then start our conversation of today's lecture, which is about free relativistic scalar field, from where we dropped at the end of lecture 2. So the topic will be called canonical quantization. Why canonical quantization? Because you explicitly break Lorentz covariance. So you pick a particular time slice, and you're going to be doing quantization at that particular time. Sorry. So recall from lecture 2 that we started with a lattice of atoms. The way we modeled them, this is a one-dimensional lattice, was by putting a bunch of atoms and connecting them with springs, right? So each of these were atoms, and then they had some sort of in equilibrium where when they were all sitting in equidistance, there was the lattice spacing, which is epsilon, which is the measure of the distance between every two atoms in equilibrium. All right. So the Lagrangian we started with had was sum over q dot square. So q of j is we're just j is the label that counts these atoms, if you recall. 1, 2, 3, da da da. And q of j is the location of the that atom. So this is the momentum term, right? Q dot squared of j, and m is mass, and this is the potential term, right? And let's say I have n of these guys in my system. All right, so the potential term, we said we want to model interactions using springs. So there will be the nearest, if you just take the potential and expand it, the second order term around the equilibrium, there is no first order term because you're in equilibrium. The second order term is the potential of a spring. That's why we're modeling it by springs. And then this was the term that we included, nearest neighbors, and this was the spring constant. There is a term I could have included there because the second order, beta over 2, beta is some coefficient, and qj is the value at each point. I did not include that for simplicity in a previous discussion in lecture 2, but today we're going to keep track of that. It will be important for us. All right. So hopefully it's clear that what I'm doing is just I'm expanding in Q, right? So I've kept everything that's second order in Q. If I terminate the action, the Lagrangian here, all I have is second order and Gaussian. Okay, one comment here. I want to say that. No, I'll not mention it. Well, actually, let me say it. So we call principles of field theory. The principles that we talked about were locality, right? Was one of the main principles that we had, and then symmetry. We're going to hit both of those two. So here, locality is the statement that first you have a Lagrangian, which we wrote down as an expression at a particular moment in time. And then you broke down your Lagrangian in terms of J, which is a notion of locality in space. Now, you included bilocal nearest neighbor terms. So there was some sort of a nearest neighbor term that you included. But the fact that you're expanding in Q in these terms is related. Yeah, I'll stop. I'll not explain anymore. All right. So just to simplify our life, we always it's easier to periodically identify and pick periodic boundary condition. So let's say you're on a circle of length L. Do not confuse this capital L with Lagrangian. I will not use this anymore. And there's lattice spacing epsilon, and the total number of atoms is L over epsilon. Right, this is the circumference. All right, so in quantization, what we do is, actually, let me not worry about this. I don't want to confuse you guys with that. In quantization, what we do is we promote Q and P, the canonical conjugate, to operators, and we're gonna basically impose the following commutation relation, IH bar. So we did that in lecture 2, and this is the form that we find, right? Q dot here becomes the canonical conjugate momentum. So this is the Hamiltonian you're dealing with, and these are your commutation relations. The way we solved this Hamiltonian model was by Fourier transform, because it's Gaussian. So we performed the Fourier transform, and then we solved the model. We found the dispersion relation that small momenta k, so this is k is momentum now, when beta was equal 0. So remember in our conversation from lecture 2, we didn't have this term. So when beta was 0, this is what the full dispersion relation, this is the dispersion relation we found. And then at small k, when we expanded it, we found a relativistic dispersion, which was omega going like k, right? This was what we found. Now, if you include the beta term, this is a homework problem, you find that your dispersion is modified by addition of this term to omega squared. And if again you take a small epsilon, a small k limit, you end up with this dispersion, where C of S is the speed of sound, right? Speed of sound was the coefficient that was sitting here. It was epsilon square root lambda over m in the previous calculation. Now here there is a new mass parameter that I'm calling little m, and this is how it's related to beta. And that mass term is going to sit like this. Now, if you set CS equal to 1, what you find is that in the infrared, in long distances, you literally find the dispersion for massive particle, right? So beta equals 0 corresponding to a massless case. Here you find a massive model. Good. Any questions? So this is going to be a homework problem. I was debating on whether I should give you this in lecture 2, but I thought it was perhaps too much. But anyway, any questions so far? All right, we said in lecture 2 that the origin of quantum field theories of infrared and condensed matter is the continuum limit. So that's when you have your circle and start keeping the circle fixed. You start squeezing more and more atoms. Or you can think of it as a model where you take a large n limit, keeping L fixed. So the circumference is kept fixed, you're increasing the number of atoms, right? In this limit, of course, the cutoff goes, the lattice spacing goes to 0. What happens is that now you end up with continuous variable Q, right? And the Fourier transform of it will basically, well, you end up with these smooth, I don't want to say this, I don't want to say this. Yeah, let me get rid of these. All right, so let me just say it. There are two things. In the continuum limit, what you end up with is your Q variable, your spatial location of atoms, becomes continuous, and it takes values between 0 and L, capital L. Now, in the Fourier space, what you're going to end up with is a discrete momenta, right, that are proportional to 1 over, that are integer valued in 1 over capital L, right? So now, if you decompactify this circle to flat space, your momenta become continuous. But I want you guys to know there are two infinities here. One of them is ultraviolet, UV. That is a setup. You first keep capital L fixed and take the lattice spacing to 0. This is a UV issue. This is an ultraviolet short distance issue. There is another one, which is an infrared issue, which is like infinities that could come from infinite volume, right? So we're going to call those infrared divergences as opposed to UV divergences. Why are we calling these divergences? Let's say, just to give you some physical intuition, let's say you're in a setup where every single atom has a finite amount of energy. Then, as the capital L goes to infinity, you pick up a volume value. So that's an IR divergence. Now, if your capital L is fixed, but you squeeze in more atoms inside your capital L, your circumference, you pick up a UV divergence. So there are UV divergences and IR divergences. The UV divergence is a feature of any continuum field theory. IR divergence is just a statement about, is your space infinite or not? Because you could put quantum field theory and find above, right? Okay, so that is why I'm writing these integrals over K as continuous. Good? Good. Your Lagrangian, now in this expansion, looks like this. I'm sorry, I changed my variable. This is epsilon. Your Lagrangian density looks like this. So it's an integral over X locality, recall, right? Q dot squared. Oh, sorry. Yeah, Q of X is your field, right? Your field is now Q of X, right? Half Q dot minus CS squared that we're going to set equal to 1. Sorry, where's the question? Oh. Minus half M squared CS4Q squared, right? So you recall that what we said is that if you pick a normalization where your CS is 1, you're going to end up with Lagrangian for free Klein-Gordon field, right? So principle of symmetry was embedded in the model in 2 ways. First, the dynamics was the dynamics such that it's local in time. That has to do with the fact that if you give me describe for me the system at some fixed time, I can evolve it with the Hamiltonian forward. So forward evolution of the well-posed problem. Okay, maybe I'm getting too much into technicalities, but in the space locality has to do with the fact that we included nearest neighbors. We did not include in our model terms that couple this atom with an atom really, really far away. That is locality in space, right? All right, so how do we solve this problem? We define the creation and annihilation operators for these K modes. Sorry. We constructed a Fock space of all Fock space, which is basically the tensor. It's basically defined by vacua, tensoring the vacua of every K mode, right? So there's a continuous set of them, or it could be discrete if you're in finite volume. This is the notation I'll use for Fock vacuum. And then you apply all sorts of AK daggers to create multiple particles, right? So you end up with, if your set of Ks were discrete, N of K1, N of K2, as the description of a particular excited state, which has N1, K1, which has N K1 particles of momentum K1, N is an integer, right? And so on and so forth. Good. We got a Hilbert space that included all particles at once. Are we good? So I just summarized lecture 2. But we did say one extra thing, which is if we could have included the beta term, and if we had included the beta term, we would have had the full, in the infrared, we would have had a massive relativist sigma. Right? Okay. So now let's take this theory and run with it, and we're going to go to D+1 dimensions. In D+1 dimensions, your Hamiltonian as an operator is going to be an integral over space of Hamiltonian density. This is locality. This is what the form of it is. I'll go through this a little bit faster, hopefully, because it's sort of clear. This K squared plus omega squared plus M squared is your dispersion. Omega k is basically energy here, energy frequency, right? So we define the creation and annihilation operator this way. This is the standard definition, right? For each mode k, we define creation and annihilation operator associated with the field and its canonical conjugate. Now that we did that, we expand the phi of x, which is Fourier transform of phi k, and this guy is a Fourier transform with this, in terms of these creation and annihilation operators, and we get these formula. Notice that I've played I'm using a funny notation. That's important. I want you guys to remember two things. Let me use a different color for this because it's important. Remember these expressions, right? Here I could have canceled this guy and this guy, but I did not. Right? So I'm keeping this expression integral of d in 3 plus 1 dimensions, d3 of k over 2 pi 3 divided by 2 omega k. I'm intentionally keeping these expressions explicitly. So remember that. I'll come back and comment on why I'm doing that. Right? That's comment number one. Comment number two is that if you recall, when we wrote down the Klein-Gordon equation and we solved it, what we found was precisely the same sort of modes. The coefficients of these guys were basically a bunch of coefficients that the solutions are plane waves, and these coefficients were all like different values you could put into get a solution. What we've done is that those coefficients have been plane wave coefficients have been promoted to operators in this example. Sorry, I don't know why I'm coughing today. All right. Another comment that I want to make is that this is all done at time t equals 0. Right? We are using the Schrodinger picture. This is canonical quantization. Right? That's important. All right. Any questions? All right, let's continue. So, of course, the commutation relations we're going to have look like A dagger and A dagger K are like this. There is this omega K that sits in there based on my definitions. And there is the Dirac delta function for K minus K prime. If you had a discrete set of Ks, this would be just a Kronecker delta. So this 2 pi to the power of d actually belongs here, so that when you integrate, you get 1. Right? All right. So what does a Hamiltonian look like? Again, I'm keeping this annoying factor like this, right? It looks like this. There are two terms to it, and what has happened is that the orders are like that. Now, by the way, this term has to be there because Hamiltonian is self-adjoint. Right? Is that clear? Good. So now using the commutation relations, you can write the second term in terms of the first term with some constant that you bring out. And once you integrate, these are things that you should absolutely do for yourself. You find an infinite constant term. You find a constant contribution to the Hamiltonian, which is infinite. So it's an infinite vacuum energy. It came from the fact that I just used this commutation relation. So I can swap the order by introducing some Dirac delta function. Now, there are two origins of this infinities. One of them has to do this delta 3 of 0. It has to do with infinite volume. That's an IR divergence. You also have this integral over k omega k. That is an infinite energy density because you have arbitrarily long momenta, large momenta, frequencies, sorry, or momenta, both, right? So even if you sit in finite volume, if you're in finite volume, this term is going to be regulated. It's going to be nice. It won't be an infinity. It will be something that's related to the volume. However, this term is going to be an infinite sum over terms that grow. So that's going to blow up. Right? So you find an infinite contribution to the energy. There are two parts to it, IR and UV. If you want to separate them in your head, think about energy density. So when you think about energy density, you only have a UV divergence. UV divergences are a lot more profound. Right? Okay. So, sorry, is the origin of this clear? The origin of this is just simply the fact that for simple harmonic oscillator, when you write the Hamiltonian as number operator plus half, right? Here you have an infinite number of these harmonic oscillators, so you end up with an infinite amount of energy. It's a little bit tricky. It's a little bit more tricky. It's not just half, but anyway. But that's what it is. Any questions? So what we usually do, I'm going to tell you something, a trick. This is to be understood as a trick that will make free field theory well-defined. It's called normal ordering. But this trick is the very first step towards a grand framework called renormalization. And it's going to be, we're going to be seeing a new principle of quantum field theory that was absent in free field. Well, we haven't discussed so far. Okay. So you could, here what you're facing is an infinite amount of energy. So you can say, oh, I'm just gonna measure energy differences with respect to the vacuum. Because it's a constant that shifts the Hamiltonian by an infinite amount. Any two states, their delta E's energy differences are well defined. And if you shift in free field theory, if you shift the energy of the vacuum, you haven't changed anything. No observable depends on energy of the vacuum. It's only a comparative thing. You can only compare two states, right? So what we do to get to this infinity is what something is just an ad hoc procedure we call normal ordering. So we define a normal order quantity to be the quantity we showed with these double dots, colon, left and right. What it does is that it says that every time you have a sequence of creation and annihilation operators, move the daggers, the creation operators to the far right. All the creation operators should be to the right of the annihilation operators. Like this term. And discard the remainders. It's just an ad hoc procedure that will get, it's another way of saying how to drop this infinite term. It takes some getting used to why this will get rid of the, well, it's pretty clear how it gets rid of the infinity of the Hamiltonian, but also it gets rid of a whole bunch of other infinities that you're gonna discover in your homework. But once you discard this infinity, you basically write the Hamiltonian as an integral over this term. This is that thing that I'm annoyingly carrying around, multiplied by this value. Now you define a number operator. This number operator is basically this coefficient that this a dagger a that you recognize as the number operator in simple harmonic oscillator, right? Multiply by divided by some volume of space. If you want to know why there's a volume of space in there, just think about these two equations. All right. So the reason we do normal ordering is that in free field theory, Hamiltonian is not the only thing that we observe. We can also observe 2-point functions, 3-point functions, 4-point functions. And all of those will have divergences as well. It has to do with UV. But the catch is this normal ordering procedure that I just described gets rid of all of them. So in free quantum field theory, we say we measure energy with respect to the vacuum, and by normal ordering, this procedure, we basically make sure that all the hard point functions are also, well, 2-point function is all you've got because the theory is Gaussian. With contraction, you're going to learn that 2-point function is all that matters, and it regulates the 2-point function as well. It will make it finite. However, in interacting theory, discarding this infinity of the energy and of the vacuum will not be sufficient. There will be other divergences appearing all over the place. We're going to get there. All right. So what we're going to do is this. These are UV divergences. The UV divergences of quantum field theory come from momentum intervals. They come from the fact that you have these type of intervals over spatial momentum. And if each mode contributes a finite amount to the quantity you're calculating, for example, vacuum energy, this quantity diverges. In fact, it doesn't have to contribute a fixed amount. If the higher and higher modes contribute less and less, but it grows like if it decays like slower than 1 over k to the power of d minus 1 in 3 dimensions, the contribution of the higher momentum modes is bigger than 1 over k squared, the integral still diverges because 1 over k2 integral of d3k diverges, oh, sorry, plus 1. My bad. Before, right? So that diverges logarithmically, right? So what we do to deal with these divergences is a regulator. We say these integrals that we had to do that will giving us divergences, we're going to cut them off at some maximum ad hoc value of momentum. We call that cutoff, right? I'm going to call that capital M. A lot of textbooks, they call it capital M, doesn't matter. All right? Is this idea clear? What we're going to say in the next few minutes is going to be a new principle of quantum field theory. And I'll try to get this very clear. I'll do my best, but it's a profound concept. So what we saw was that we had UV divergences, and we want to get rid of them. I haven't explained how to get rid of them. I'm just telling you, sort of like priming you guys in advance for our discussion of normalization. So let's see how these UV divergences will regulate the cutoff will regulate the vacuum energy. So this is what the vacuum energy was. This is the IR divergence. We calculate vacuum energy density. This is what the expression is. So omega k for a massive particle is like this, square root k squared plus m squared. This is your integral that I cut it off by some maximum norm of spatial momentum k. Here in this, because we're doing canonical quantization, momentum means spatial momentum, right? So far, in this lecture so far. So you do the integral and you find that it goes like m to a power of 4, the cutoff, the cutoff scale to a power of 4, right? All right, so we did some calculation. We found something that depended on m. Here is a principle of quantum field theory. If you don't want to produce garbage, if you want to have a sensible theory, your physical quantities must be independent of them. Otherwise, we're talking nonsense because you might regulate it differently than I do, and we don't have a theory that describes it, right? So what we do is we introduce a parameter m called cutoff that explicitly gets rid of infinities. Because we introduce it by hand, it's ad hoc, it's random, it's man-made. A lot of calculations will depend on this parameter, but not all calculations. Anything that deserves to be called physical must be independent of it. This is a physical principle. Good? So this is a new principle for quantum field theory next to the two other principles that I discussed, right? Locality and symmetry. If I want to formalize it in words, we introduce a cutoff and in the presence of a cutoff, we need to prove our physical quantities are independent of that for a sensible theory. Now, what is the physics behind this? What's the physics behind why does this even make any sense physically? The idea is the principle of separation of scales or renormalization in quantum field. Recall the calculation that we're doing. Recall the analogy with lattice. In the example of lattice, the cutoff scale puts an upper bound on provides some sort of a the lattice spacing provides a cutoff on the momenta. If I'm doing a calculation that's supposed to be infrared, low energy, if I introduce a cutoff that's very, very large at very, very large energies, my physics should not depend on the cutoff. Now, how is this a principle? You know this as a matter of fact, because when Newton built his theory of F equal ma, his formula, his observables of the theory did not depend on quantum gravity, arbitrarily small, deep in the UV scales. Newton didn't need to know about what the nature looked like at quantum gravity scale at very, very high energies. Newton could construct a model based on which we build bridges and houses. The model works because all the physical things it describes are independent of the physics deep in the UV. We don't really know what the physics deep in the UV is. So you might as well say there's nothing in the UV, just cut it off. But the point is that deep in the UV, whatever is going on is going to be decoupled, unrelated with the infrared. This is a principle of separation of scales. So physics organizes itself in terms of energy scales. That's why we think it's a sensible thing to do, to put an arbitrary cutoff at very, very large scales, and our physical quantities will not depend on this. Any questions? This is a principle, the same as symmetry and the same as locality. Nobody told you that all theories must follow these, but it's a principle we use to construct a large class of theories, and these class of theories describe the nature around us. It's an axiomatic way of thinking about stuff. The same way that there are some funky, really crazy theories that are non-local, violate locality principle. There are also theories that are non-renormalizable. They could not be managed in any nice form. They don't have a separation of scales. But luckily, the nature around us is renormalizable. There's a separation of scales. This is I guess, sheer magic, if you wish. There was no reason. Well, I'm exaggerating a little bit. But at this point, you should be just surprised every day that your car, your cell phone, everything works, because we still haven't discovered physics at like quantum gravity scale, Alpine scales, but we could do physics, even though we haven't discovered it. All right. So now we come up with a better, this is sort of like a framework to think about physics, not even field theory. It's called effective field theory. The idea is that any theory will naturally come with a cutoff scale, right? There will be always an energy scale associated with any theory, that this theory will hold at energies way below this. Special relativity, Newton's physics was an effective field theory that holds for velocities well below speed of light. Newton's mechanics is not incorrect, it's an effective field theory. Special relativity has an extended realm of domain of that is applicable, but it still fails at very, very large energies, could fail at very, very large energies, because we don't know, we have to deal with quantum nature, right? All theories we deal with are effective field theory. So what is an effective field theory? Effective field theory is a theory It's a quantum field theory where there is a cutoff that's naturally included as a part of the definition of the theory. So if you have an interacting quantum field theory and there are these divergences as you bring the 2.5 next to each other, those divergences, you can't get rid of it, right? Normal ordering in free quantum field theory gets rid of it, but in interacting theories, you can't get rid of it. So there's a procedure we're going to discuss in detail. It's called renormalization, and it works if your effective field theory follows this principle of separation of scales. It's a mechanism. If you are lucky that you have this principle, then it's a mechanism, a framework that we've invented that will get rid of these divergences. All right. Okay, enough philosophizing. Is this clear? Are there any questions? I'm going a lot slower down this one. All right. Good. So now let's discuss one particle states. Actually, let me pause a little bit more. Is this clear? So we have set 3 principles of quantum field theory, and I'll not introduce any more principles. These are the 3 principles: locality, symmetry, and separation of scales, renormalization. But most of quantum field theory is about understanding what these principles mean. All right. One particle states. Let's go back to our quantum field theory Hilbert space. We said that we had a Fock vacuum and we had these creation operators. And if you applied once with momentum k, you have created a single particle momentum k, which is analogous to the vector ket k in single particle quantum mechanics. So the Hilbert space of single particle quantum mechanics is sort of a superposition of these A dagger k's only with one insertion, but different case, right? Now, we said in previous lecture that if you have a massive particle, K cannot take all arbitrary values. Your K is restricted to this, in this way. Your 4 vector K mu, energy and K are related, right? And this is the range that you should have. First of all, energy has to be positive, right? There's a step function for K0. Frequencies have to be positive, and then you should be on shell, right? Now I'm going to explain to you why I was annoyingly carrying these combinations around. What you should be doing in a covariant quantization, without picking time and space, separating time and space, picking a particular time, you should be integrating over 4 momenta, or d+1 momenta, k mu's, and put in this constraint in there. That's what you should do. Well, do that integral. This is the expression you're going to get. Now, why is this expression good? Because it's Lorentz invariant. Under Lorentz transformations, this integral remains unchanged. And that's important. That you could see from this definition. It's pretty clear from this definition. Because Lorentz transformations move you around over here and move you on this, right? Shift you along this. And I've integrated over the whole thing. It's like if I have a circle, if I integrate around the circle, the result is going to be rotation invariant. Said differently, this is hard measure. Mathematically, it's a hard measure. But, all right, that's important. That's very important because now, if you look at the expression that we have for phi of x, apply a boost transformation, a Lorentz transformation to x. That's supposed to be captured by the following unit terms. Because this beast is Lorentz invariant, all that's happening, and then x, all that's happening is basically a, k goes to a of lambda acting on k. So you end up with these simple relations, as you should. This is crucial. This is the reason I was keeping this one over this particular annoying factor 1/2 omega k. The theory is covariant. So even though we're doing canonical quantization, we should be careful. We should be, I mean, you could simplify your life by keeping covariant forms, right? Because you've explicitly broken Lorentz invariance. It's a symmetry of the theory. To help you organize things, it's a lot easier to keep these Lorentz invariant combinations. So this is analogous to one particle quantum mechanics, relativistic one particle quantum mechanics, in the following way. That if you have one relativistic particle that you were quantizing quantum mechanics, no field theory, then that just means that U of lambda is this unitary that acts on your K vector and just does the Lorentz transformation. Okay. Now, every time in quantum field theory, in canonical quantization, if you see there are like omega K's floating around, that's because we are intentionally writing things in this covariant form. So turns out that the right way, the good notation convention for normalizing one particle states is this way. There's this extra 2 omega K. This is not surprising at all, actually. Now, the one particle Hilbert space will have an identity. There's a projection to one particle Hilbert space. That projection is precisely this, with this Poincare, this Lorentz invariant measure. You could just test that by applying this identity in the middle of this. So this is a resolution of identity for the one particle Hilbert space. What we are doing is that we took our Fock space, we identified single particle states, right? And we're matching that with the Hilbert space and the good old quantum mechanics quantization of a single particle in quantum mechanics and the Hilbert space in common. This is the translation. This is the language. This is the dictionary that goes between the two. So if you look at in the one particle Hilbert space, this is the overlaps that you're going to get. So basically phi of x acting on the vacuum of the Fock space acts like the ket x in quantum mechanics, right? Because we said that this is basically this is phi of k. Good. So if you ever find yourself confused about how Fock space second quantization relates to good old quantum mechanics, this is your dictionary. Any questions? All right. Now, in quantum mechanics, we are very familiar with Schrodinger picture. Whereas if you pick a typical quantum field theory book, everything is done in the Heisenberg picture. So let's get this out of our system. Discuss Schrodinger picture in quantum field theory for one slide, and then we'll move on. Turns out that it's not the simplest way of doing things, and hopefully you know why. Actually, I just argued to you guys why Schrodinger picture is not a very good, convenient framework. It's a correct framework, but it's not a convenient framework. Why? Because you have to pick a particular time slice. You will break Lorentz, your formulation is not manifest the Lorentz invariance. Right? That is why if you pick a random book on quantum field theory, everything is done in the Heisenberg picture. You could use Schrodinger picture, it's just cumbersome. It's a little bit annoying because you have to make sure you carry around these expressions that might, from the three-dimensional point, from the canonical quantization point of view, they look arbitrary, but they are actually Lorentz invariant or Lorentz covariant. Okay, but let's just say a few things about wave functionals. So the same way that in quantum mechanics, psi of x is x and some psi, some state psi, and we said the analog of ket x in quantum field theory is phi of x. So your wave functional is going to be the, say, vacuum wave functional is going to be the overlap of Fock vacuum with some ket which is labeled by phi of x, a function. Now, this ket that is labeled like that will have to satisfy this equation, which is the analog of this. If you want to know what these states are, they're related to coherent states. Be my guest. We'll learn about them. They're fun. Actually, calculations of entanglement, any calculation of quantum field theory that involves a particular time slice could be done in this framework and often is done in these type of frameworks. For example, entanglement entropy calculations. So some calculations, we do use this framework. But in Schrodinger picture, wave operators are time independent and wave functionals evolve in time. In the Heisenberg picture, operators like phi hat will be time dependent, right? So in canonical quantization, all these expressions that I wrote here, let me get one of them, for example. Yeah, these expressions, I pretend that these are time independent. I just put spatial x and p, right? I was doing everything in space. So that is, I was working Schrodinger. In the Heisenberg picture, I have to talk about operators that depend on time. When I was talking about commutators, that is equal time commutators in the Heisenberg picture. All right. So in the Heisenberg picture, operators evolve in time and wave functionals are time independent. So your operators O of Heisenberg, little h for it. I'll not use this capital H, I'm just using it for now. All my operators are going to be from now on are going to be Heisenberg. It's a function of space and time, x0, and it evolves in the following way using the Hamiltonian. All right, so here's the, what is this called? The Heisenberg equation? It's the Heisenberg equation? Yeah, it's called the Heisenberg equation. This is the analog of Schrodinger equation in the Heisenberg picture, right? All right, that tells you how operators evolve in time. So now your creation annihilation operators depend on time. If you want to know what your annihilation operator at time t is, you just have to sandwich it with Hamiltonians. And then you use the BCH, Baker-Hausdorff-Campbell, that expands such expressions, and you show that it's basically it's related to the annihilation operator at time 0 by just a phase, the coefficient of which is the frequency of the particle. These are things that you're going to do in your homework. Oh, sorry. So your phi of x and t is going to be an integral over, again, this Lorentz invariant measure, ak of t, like that, right? Because these are the operators. The way you evolve phi is by sandwiching the unitary. The unitaries acts on operators. These are the operators, right? Therefore, what happens is that, well, this guy pops out of this term, e to minus I omega t, pops out of this one, e to I omega t, and you can write them in terms of these phases. They used to be space direct products. Now they are becoming k mu x mu, k mu x mu. So we still have equal time commutators of the Heisenberg operators written this way. What is the commutator at different times? I invite you guys to think about this. And I already said this in quantum field theory, we're almost always using Heisenberg picture. in this course as well, except for in scattering theory, which you might remember from quantum field, for quantum mechanics as well, we often work, it's more convenient to work in the interaction picture, which is neither Schrodinger nor Heisenberg. Actually, a lot of quantum field theory is done, perturbative quantum field theory is done in interaction picture. All right. Any questions? This is a natural stopping point. So what did we do? We started by the summary of lecture 2 with a bunch of atoms sitting on a lattice. We took a continuum limit, low energy continuum limit. We discovered a massive free scalar field in 1+1 dimensions. You could repeat this in a higher dimensional lattice. You're going to discover a d+1 dimensional massive scalar field. Okay. This is solving the Klein-Gordon equations. We solved this by Fourier transform. Now, when we quantize this, there will be creation and annihilation operators associated with every spatial momenta, right? There is infinite of them, and each of them contribute to the energy by a fixed amount, the same way that in simple quantum harmonic oscillator, the energy of the vacuum is half omega h bar omega. Here you have the same situation, so you're summing over half omega k squared with k squared plus m squared, and that sum diverges. That was infinite energy. And in free field theory, we get rid of this infinity using an ad hoc procedure called normal ordering, which is basically saying that whatever operator you have, always make sure that A daggers are to the right, and creation operators are to the right of the annihilation operators. Is that what? Yeah. Or wait a second. Sorry. No, the other way around. Yeah. Okay. Did I say it incorrectly first time? I don't recall. Anyway, now we said that this principle is not going to work in general for interacting theories, so that's why we have renormalization. We introduce a cutoff on energy momenta, spatial momenta, and that regulates our theory, and physical observables, physically relevant quantities will be independent of this cutoff. We discussed one particle Hoover space. The one particle Hoover space, we matched it with the good old quantum mechanics things. And then we talked about the Heisenberg picture and how operators evolve in time. Are we good? Any questions? Okay, in the remainder of this lecture, I'm going to pick the example of complex scalar fields. So the reason is that we're going to discuss symmetry. So in the previous example of a real scalar field, there was no clear symmetry except for space-time transformations. But as you recall, if I pick a complex scalar field, I have a U1 symmetry, right? Okay, so here it is. The Lagrangian for a complex Lagrangian density for a complex scalar field is del mu phi dagger, del mu phi plus m squared phi dagger phi. You calculate the canonical conjugates, phi dot and phi dot dagger are going to be the canonical conjugates. You have a symmetry, which is U1, right? And there's a U1 charge associated with it. It follows from Noether's first theorem. You also have a Z2 symmetry that I hadn't mentioned in the past, but now is the time to discuss it. It swaps phi and phi dagger. It's convex conjugation. There's a charge associated with it. It's called C. I mentioned this charge in passing a lecture or two ago. Charge conjugation. All right. So let's write down Hamiltonian density because we're going to canonically quantize it. It's going to be pi dagger pi plus the gradient of phi dagger dot gradient of phi. You have these commutation relations. Hopefully these are not mind-blowing. Phi and pi are canonically conjugate. Now, because we have 2 degrees of freedom, we will have A and A dagger and B and B dagger. So we have a pairs of creation and annihilation operators. Like for each, we have a pair of creation and annihilation operators for one of the modes and the other one or the other one. It's like a complex field could be written as phi 1 plus I phi 2, right? There are a pair of degrees of freedom. All right, so these are the definitions for phi and phi dagger. Now you normal order this Hamiltonian, and what you get, this is again that Lorentz invariant expression, is you get two number operators. One is counting the number of A-type particles. The other one is B-type particles. Because you have the pair, right? The pair of degrees of freedom. Is this part clear? Am I going over this too fast? Too quick? Okay. So you have a pair of these degrees of freedom. So you have a pair of your Fock space will be labeled by a pair of such number operators. You have a U1 conserved charge, which, like any other observable, has to be normal ordered, right? So it's an integral over space of phi dagger phi dot minus phi dot dagger phi. If you write it in terms of the A dagger and A, you end up with after normal ordering, you end up with an expression which is the difference between the number of A particles and the B particles. The B particles are going to be called the antiparticles of the A particles. What we're learning is that both particles and the antiparticles are going to contribute to the energy because we're adding the Hamiltonian was just the numbers being added, but they have the opposite charge because the total amount of charge is going to be one minus the other one. So in free field theory, the total number of A and B particles is conserved because Hamiltonian is just that. But the moment you introduce interactions, like for example, V of phi dagger phi, the type of interaction we introduced in the past, this will no longer preserve the number of an arbitrary potential will no longer preserve the total number of particles and antiparticles. However, you still have this symmetry, phi dagger phi. You still have the U1 symmetry. So the total number of particles is no longer conserved, but the total number of particles minus antiparticles should be conserved. So you could create a pair from the vacuum, but it should always be particles next to an antiparticles. You can never create a pair of A particles or pair of B particles. You always have to have particle and antiparticle. And it has to do with this U1 symmetry. So in summary, A particles and B particles, they are antiparticles of each other, right? They both contribute to the energy, but the charge is the opposite. Now, which one I pick to be the particle and which one to be antiparticle is arbitrary. It's up to me, right? And that's just a statement that I have a charge conjugation symmetry, right? So phi, this charge operator acting on it, will send phi to phi dagger. It produces a Z2 symmetry. Is it clear why? Because sends phi to phi dagger and phi dagger dagger is phi again. So the eigenoperators of that are +1 or -1. Something could be either symmetric under C, because C squared is 1. The eigenoperators of it are going to be +1 and -1, self-adjoint. Right? Good. So this is how it acts on the particles. It sends particles to antiparticles, swaps particles and antiparticles. And if you just take the charge operator, stick it in there, actually, let me show it to you guys. Where was it? Here's the charge operator. If you swap the A and B index, Q goes to -Q, right? So charge is flipped, but all charges are flipped. So this is a statement that in our universe, at some point we decided that electron is negative charge and proton is a positive charge. That was arbitrary and it doesn't matter. We could have picked proton to be negative charge and electron to be a positive charge, and nothing in the universe would have changed. The current is also the same. The current is just a local expression for Q. right? That's also picking a minus sign. So now, if you're in electromagnetism, this is how the photon is coupled to your charged particles. So if you want this whole thing to preserve, to be symmetric, this is a term in the Lagrangian, Hamiltonian, Lagrangian. If you want this to be symmetric under this charge conjugation, if under charge conjugation, J picks a minus sign, A should also pick a minus sign. So photon should also have this -1. And all the particles in nature, they are going to be, if your action has the symmetry, all the particles in nature are going to be always labeled, you could always label them by plus or -1 corresponding to this Z2 symmetry. Okay, so let me summarize. What we did was that we after the discussion of real scalar field, we picked the example of a complex scalar field. Now there are two symmetries that appear. One of them is the Z2 symmetry, which is swaps phi and phi dagger, right? And the other one is a U1 symmetry, a phase, right? All right, I'll not make there's room for a comment, but no. We said that, well, there are charges associated with both of them. There is a charge associated to the U1. Well, sorry, we said that we have a pair of degrees of freedom, and one of them is particle, the other one is anti-particle. They both contribute to the Hamiltonian, so they both have positive energy. However, they have opposite charges. One of them is +1, the other one is -1. And charge is basically, the total charge is the number of particles minus antiparticles. Because that number has to be conserved, in an interacting model, you could create particles and antiparticles, but you always have to create them in pairs. Particle-antiparticle pairs. All right. That is basically all we said. All right, any questions? It was either very clear or very unclear. I'll pause for a little bit more. All right, now I'll end with a summary, and summary emphasizing again on this idea of renormalization. So in part 1 of the course, we started with classical field theory. In classical field theory, we founded everything on the principle of locality and symmetry. I made a quick comment in last lecture that was ultraviolet catastrophe. Classical field theory is ill-defined because it has arbitrary UV modes, and that is precisely these UV divergences that appear here as well. Well, sorry, I should say it that way. That's related. It's related to that. So in this part, as we quantize as we quantize field theory, we discovered a new principle that was renormalization and separation of scales. The idea behind this principle was that when we were calculating energy or a whole bunch of observable things that we thought were observable, like 2-point functions of the field, we saw that they're all divergent. In free field theory, there is a trick which is called normal ordering, which gets rid of all of them in one shot. All right, but just saying that we only can measure the differences with respect to the vacuum, difference of the energy with respect to the vacuum. However, this principle in interacting theories is more complicated. It's not easy. You cannot just get rid of all of them in one shot using normal ordering. It's a little bit more tricky. And then we said that there is a principle called renormalization, that is everything in the physical should be independent. every theory comes with a natural scale that defines this regime of validity. It's well below that scale M cutoff scale. And this is an effective field theory, and all the physical observables should be independent of that. Eventually, in this course, we're going to come to a point where we discuss how we get rid of these infinities, what theories are normalizable, what theories are not normalizable. But keep this in mind. Renormalization procedure is going to involve two steps. You always introduce a cutoff, and then you shift things by infinite amounts. Right? That's what we did in the case of normal ordering. You shift things by an infinite amount. A theory is nice and renormalizable if you could do such shifts a few times, like once, twice. Here in free field theory, we did it once and we're good. Once, twice, three times, a fine number of times, and then it will be, everything else is going to come out fine. If you need to redefine infinite number of variables, that theory is non-normalizable. This is a cartoon picture, but we're going to get there. All right, any last questions?
If the photon has c equals -1,
yeah.
What particles have c equals +1?
Yeah, very good question. What particle has c plus 1? Well, it has to be invariant under the transformation that sends the particle to its antiparticles. So a particle that has c equal 1 means that it's its own antiparticle. Do you know of an example of such a thing?
Neutral particle.
Sorry? Yeah,
neutral.
Charging particles. Yeah, things that are not charged. Sorry, I said the poorly. I said incorrectly. Let me correct myself. Let me correct myself. It's not about it has to be its own antiparticle, because if you have a particle that is its own antiparticle, now you couple it to something else, right? C of that something else is going to be 1. So here, C of photon was -1, right? Because it was coupled to J mu, and J mu had C equal -1. Right? That is the proper way of saying it. So how does that work? Yeah. Okay. For example, let me just say it a little bit differently. If you wanted to couple two real scalar fields, right? The coupling is going to be some J and phi, right? Those things are going to have C equal 1.
Yeah, because I guess my confusion was just that like the photon is already chargeless, and is its own antiparticle.
Yeah, that's right.
Right, but it's still C-1 because it's coupling to current, which
yeah, exactly.
Okay.
The antiparticle and particle is about the phi, the charge thing. Yeah. Yeah, I said that poorly at first. Okay, any other question? All right. If there are no questions, this is the end of this lecture. And yeah, thank you so much. We're going to continue with quantization in the remainder of the course. Have a nice day, guys.